Hello everyone, I'm Mark. So my day job is computer security, hence the sort of B-sides interest. But I like playing with robots as well. And so because events like this are kind of weird and you can go kind of off-piste, I thought, well, let's do that. And it worked really well last year, so I thought I'll do it again. But this time, I thought what I'd do is bring stuff so that you can have a go yourselves, right? So, when we get to the workshop-y bit, and we don't have to be too strict over the separation between what's talk and what's workshop. In fact, Sam called it sort of a talk shop. I think she wanted a bit of both. And what I've done is I've brought some stuff. So here are some things, and here are some more things, and here are some things, and even more things. But most importantly, I brought actual devices you can play with. How many are we here? 7. There's enough for most of you to sort of have a play with one of these. Who's got a laptop out of interest with them? Does the laptop have a USB port?
Can do.
You can do, okay. So, yeah, you can plug stuff in and have a play. And if, when you've finished, you want to take one of these away with you, I've got enough for most of you. And a tenner gets you one of these and a prototyping board. But first, I'll sort of introduce what I'm talking about. I started playing with computers when I was quite little. My dad was a science teacher, and in the 1980s, if you were a teacher, you got a subsidised BBC microcomputer that you could learn to program on. The idea being that if you learn how to use the computer, you could teach your pupils at school how to use the computer, and then all of a sudden, eventually all of the people in the UK would soon get digital skills. The plan didn't work brilliantly because most teachers didn't learn how to use them, but it worked all right for me. There was something really exciting about that first computer I had. By today's standards, it was absolutely pathetic. It had an 8-bit CPU, a 6502 CPU. It had 32k of RAM. I was really lucky because we had a disk drive and a colour monitor. So this was amazing. And sorry, I'm repeating myself from last year. I'm really conscious of this now. One thing I've noticed is, as the years have gone by and the computers that I use get better and better and better, they're not as fun. And I'm like, why is that? Why is it that the machines I'm playing with now just don't have the same excitement as these first ones that I used? And I think there are two reasons, right? The first reason is that we get really, really accustomed to the technology that's around us. Right, I've got a really bad car at the moment. I bought it because my oldest son is learning to drive, and it's got more powerful computers in almost every part of it than the computer I learned to program on. The brakes have got computers, the engine's got a computer, the in-car entertainment's got loads of computers, and it's like a hatchback that my kid's learning to drive in. And my phone is a powerful computer. It's, several times more powerful than the computer that sent the Apollo missions to space. And everywhere we go, we've got computers. So that's the first thing. We get really, really used to them. The second thing, and this is a bigger problem, is that the computers we've got today are really hard to play with, right? If you want to actually do something with a machine, you've got to, well, first of all, figure out how, yeah? And then you've got to go and find some SDKs or programming tools. You've got to install them. You've got to figure out how to use them. Whereas when I had the BBC microcomputer at home, I'd turn it on and it'd go boop, boop. And then it'd say on the screen, BBC microcomputer 32K, and I could start typing code there. The actual operating system command line was a basic REPL environment. You could write literally programming commands there, and they'd work straight away. You don't get any more accessible than that, right? And, sure, some of it was inconvenient. Like if I wanted to save my work, we were lucky, like I said, we had a disk drive. You might have to use a tape, put a cassette in the machine and blah, 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 blah. But the point was, from turning the machine on, how to play with it was right in front of you. And we've lost that, right? But something's happened over the past few years, which is that the sorts of machines that are really easy to play with have become much more accessible. Okay, so who's played with a Raspberry Pi before? Show of hands. Okay. Here's a Raspberry Pi. This is a Raspberry Pi 3, I think. I've got an Ethernet power over Ethernet shield, so I can power it from an Ethernet port, which is cool. This is a Raspberry Pi Zero. These are tiny and quite cool. On this thing here, that blue thing is an Arduino. Okay, and then what we're going to be playing with today are a different sort, which are the Pi Picos. It's a Raspberry Pi 2040 ARM-based microcontroller thing. And the best thing about these is that the prices have got ridiculously cheap. When I first started playing with Arduinos, they cost about 30 quid each. Raspberry Pis, the first ones were sort of £20-ish. The Zero's a bit cheaper, but the Pico, you can get the basic version for about a £5, which, you know, for having a play with a computer that you can really easily do stuff with is quite exciting. So that's the why. We're going to try and sort of rekindle some of the sort of immediate wow factor of playing with a computer. And then there's another aspect to it as well, which is that we want these computers to do things, right? So what's a robot? Maybe you tell me what they think a robot is?
Yeah, it does stuff like processing.
Yeah, so it's a computer that does stuff. Like, generally we use it to mean like a computer that interacts with its environment in a non-specialised way, right? So, you know, you might have a robot on the production line and it might be able to do a bunch of different stuff. But like, you know, when you're being sort of fairly loose with your definitions, a robot could be something like the thing on a production line in a factory, or it could be like your washing machine, because that's a computer that does physical stuff with its environment, right? Or your printer, I guess. But the more general purpose it is, the more roboty it is when we talk about it, I suppose. And I've built a load of these things. Some of the first things I built were really, really simple. I was quite into making little remote control toy type things like this. I made a doorbell that when you pressed the button, it took a photo. This was before the whole sort of creepy doorbell proliferation. So when I made mine, it was more a comment on the sort of banality of stuff that people put on social media. So you press a button and it would send me a tweet that said ding dong and put a picture of the person at my doorbell, right? A lot less creepy than a Ring doorbell in that, you know, it wasn't recording all the time, but a lot more creepy than a Ring doorbell in that put their face on Twitter. But that's a different story. And I've done things like automated things around my house. I've made a door on the chicken coop. I have chickens because we live in the countryside, that opens when it's daylight and it shuts when it's dark. And then you can sort of take the ideas a little bit further and start adding hardware to do other things. Like in here somewhere, I've got an RFID tag reader, and the chickens have got little RFID rings on their feet. And so you can do things like only shut the door when it's dark and all the chickens have gone inside. And if they haven't, go out and figure out what's gone on with them and that sort of stuff. And it's really good fun because you're not limited by what a manufacturer has told you can do with your stuff. You've got the possibilities that your imagination and the hardware that's available to you can enable you to do. Oh, here we are. So this little thing here is an RFID reader on the Raspberry Pi Zero. So that's the idea, right? Who's done any kind of physical computing before? Is anyone? Okay. So what sorts of things have you done then?
No, I was just going to say, could you actually define physical computing first? Cause
well, so like a computer that interacts with its environment through non-standard hardware.
Oh, well, I think that the very basic things like turn on LED light and stuff like that.
Okay, brilliant.
First thing, because smart mind anyway.
Yeah, so probably we're going to not get a huge amount past that because obviously some of the people here are completely new, but you can have a go at doing some more interesting stuff if you want, because I've got a load of stuff here. So, yeah, the plan for the next... How long have we got for the talk? Is it half an hour? Okay. Until you get kicked out. Until I get kicked out. Well, the thing is we can do the workshop stuff as well, so like, you know... what we're going to do is we're going to pick a device. We're going to, I think, go with this one, but we could use that as well. And we're going to do, first of all, some simple sort of output and some simple input. And then we're going to join the two together and then we'll get to more interesting stuff like analog input and analog output and that sort of stuff. So that's the plan. Does that sound good? Sound like a good plan to everybody? Okay. So first of all, apologies. Actually, this is a cautionary tale, right? You know how whenever you're doing talks and stuff, they tell you to make sure you've got everything prepared well in advance and that you've rehearsed your talk and you've done your slides and all that sort of stuff. I never, ever, ever do that. Usually, if I'm doing a talk, I'll be doing the slides when I stand up. And this time I thought, you know what? I'm not going to do that. I'm going to have all my talk ready. And so the security talk I did earlier on browsers and security, I've got all that sorted out. I've got my demos working. And I went to pack my bag yesterday, and the phone, the old Samsung Galaxy S7 I used for my demo last year, wasn't working. And then I got here and turned my Linux laptop on, and that had broken as well. And so the lesson is, don't bother getting stuff ready, because when you do, everything goes wrong. Anyway, and so I did want to show some slightly more advanced use cases. I brought the Lego robot last year, and I wanted to show you a machine learning demo using the same hardware, but we're not going to do that today. I'm speaking at DDD in Nottingham next weekend, I think, so I'll do it then. So if you happen to be around, come along. Right, but let's get started. Okay, so we're going to start off. In fact, what I'll do to make the workshop easier later on, we're going to get a sealed device out of a packet, and we'll go straight from the outset. What do you have to do to set one of these things up? Okay, so this is from SB Components, a Raspberry Pi Pico. It's in a sealed packet. So I've got to figure out how to get in. And then what we're going to do is we're going to plug it into the computer and start using it. Okay, so if you've got a laptop and you're going to be having a go later on, it might be worth doing this now. If you get your laptop open, make sure you've got Python 3.10 installed and install the Thonny Python editor. Okay, because it's the easiest way of getting this stuff running. So here's Thonny, and I've set up my Mac to run Python 3.10 so that it works. And I plug it in, and actually plug it in holding down the boot cell button. And when I do that, I get the option of installing. Can you all see the screen all right there? I get the option of installing stuff. And do I have mobile phone coverage? I do. So probably I can just install MicroPython and that should work. No, that's not working because I haven't got a good enough internet connection. So there's another way you can do it, which is that when you plug a device in for the first time and you hold down that button, it tells the host machine that there's a USB storage device. And to set up the runtime, all you have to do is install the Pico MicroPython firmware on the device, literally by copying the file. You can download this from raspberrypi.org. And once the file hits the file system, the device realizes it's been updated and it restarts. Okay? So hopefully, there we go. And I've got a Python interpreter now, and I can say, hello. And that code there is actually running on this microcontroller. Okay? So what we're going to do here is, first of all, we're going to start with a blinking LED example. And I'll talk through what the code does, but just to prove that it's running on here, I'm going to run the current script. Actually, let's get a camera up and running on here. So you can see the board there, and when I press play on the IDE, where's the LED on there? When I press play on the LED, there we go. See the LED blinking on and off. And what I can do is I can play with this. I can say, okay, actually I want to double the frequency of this just to prove that it's actually happening live. Okay, so that works. We've got that thing working. So let's talk through what's going on with the code here. So we're importing some Python libraries for the pin object and the timer object. We're telling it to create a new pin with the built-in LED that's on the board. We're setting up a timer object, and then we're initializing the timer in a periodic mode, so it's setting off periodically at a frequency of 5 times a second. And every time the timer runs, it calls the tick callback, which is here. And then in there, all we're doing is we're saying there's a global object called LED, pull that into scope, that's this one here. And then I want you to toggle the LED, I want you to turn it off if it's on, and vice versa. Okay, really, really simple. We've got something immediately already that turns a light on and off. Right? Yay, fantastic. Okay, so now what we're going to do is we're going to take it one step further. It's nice being able to use that LED. What if you want to use a different LED? And so what we can do there is I've put an LED on a board here. Okay, and what we're going to do is run the same code with a small modification to make it run on the other board with the LED plugged in. Now this one here, rather than using the built-in LED, it's setting up a pin number 15, which if you look at the device, they're labelled, look, on there, and on the top, some of them are labelled by number. So pin 1 is here, so pin 15 will be about halfway down. Okay, so let's try this demo. We do the same thing as before. Let's create a new one because it's expecting it to be saved. Actually, don't need to save it, it's fine. We'll just run it. Hang on. I know what's happened. There we go. There we go, and there you go. And we can really show off by saying, actually, there are 2 LEDs here. Let's flash them both at the same time. So we're going to do that. There we go, got 2 flashing on and off. But this code is showing something else as well, which we'll get to in a second, which is that here on this board, that little black thing there is a switch, it's a button. And what the code here does is we've set up the pin. That's the LED that's built in. That's the LED that isn't built in. So we set up an output pin for an LED, and we set up an input pin for the button. And then when the timer runs like it did before, we're saying if the button is pressed down, I want you to toggle the LED that's on the board, but always toggle the LED that's built in. Okay? And so when we run the program, unless I press down the button, the LED that's on the board doesn't do anything at all. But when I do, it's blinking on and off at the same rate as the other one. And I can have them either out of sync like that, or in sync like that, just by letting go and pushing down the button. Okay. So that's kind of like the sort of hello world of microcontroller stuff. We've got really, really basic digital I/O. We've set up a pin for input, and we've set up a pin for output. We've read the state of the input, and we're using that to make a decision in our program, and then we're using the output to allow the device to interact with its environment. Okay, does that all make sense? Is that all clear? I've explained that okay. Brilliant. Okay. Before we move on, I just want to talk about different types of devices. Does anyone know how a Raspberry Pi Pico like this, or an Arduino like the one on this robot, does anyone know how those differ from something like, for example, a Raspberry Pi computer?
The Picos are more, as you said before, microcontrollers, while the Raspberry Pi has a full operating system usually.
Exactly, yeah. So a Pico and an Arduino, they're microcontroller boards. Okay, so what they allow you to do is they allow you to load very low-level code straight onto the storage of the device, and it only does that one thing. Yeah, a Raspberry Pi, so a Pi Zero or a regular Raspberry Pi like this, it's very much like a regular computer in that it's got an operating system installed that allows you to do various high-level things with fancy hardware. They've got networking stacks, they've got a full Linux kernel, they've got various different types of storage and all that sort of stuff. The USB connectivity, there's a built-in bus for a camera module and all sorts of stuff like that. So this is much more akin to sort of the computer that you'd use at home, your desktop computer or your laptop. Hardware-wise, it's actually very similar to your phone. So generally speaking, a microcontroller is simpler. You're working closer to the hardware. A Raspberry Pi more like a normal computer, and so you get the benefits that you get from running a high-level operating system, but it's much harder to do some of the low-level stuff, and I'll get to that a little bit in a moment. I use different things for different purposes. For example, the doorbell I made that when you press the button, it took a picture of you. That obviously needed to do network stuff. It needed to call the Twitter API. It needed to do camera stuff because it needed to take a picture. And so a Raspberry Pi was really nice for that because it's got all of that stuff built in. When I'm making use of computers for simpler tasks, like, for example, the chicken coop door opener, it doesn't need to do any of that external interaction at all. So you can get away with something that is much simpler. But also, there are some other advantages to using one of these. The big one is it's much easier to do analog inputs, which we'll get to in a moment. Okay. So sometimes when I'm building something, I'll use both something like this and something like this in the same device. One example of that is I made a incubator for hatching chicken eggs, and it turns out it's really, really important when you're incubating eggs that both the temperature and the humidity are absolutely spot on. If you get the temperature, a degree wrong in either direction, if you get the humidity wrong, it kills the chick inside the egg before it hatches. And so you can get little sensors like this, which will do temperature and humidity sensing for you. It's much easier to make this work with your microcontroller than it would be the grown-up computer. And so sometimes you'll do something like you'll have this attached to this, and then some kind of link between this and that, and we can get to that in a moment. Okay. Any questions on the different types of boards and why you might use each? Okay, good stuff. Well then, so let's move on. We've used digital input and digital output, so that's where you've got something like an LED, which is either on or off, and something like a switch, which is either being pushed or it isn't. Right? There's a connection or there isn't, and we've got an example that shows both of those. So let's do something a little bit more complicated. What we're going to do this time is we're going to make use of a script that allows us to read an analog input. So I'm going to need a controller and I'm going to need a board of some kind. Let's use this one over here. Actually, we can use this one again. Actually, I'm going to get another board out. So one thing to bear in mind when you're doing this with these devices is that a lot of the pins can be used for both input and output, but almost always there's a limited number that you can use for analog input, and there's often a limited number where you can do what's called pulse width modulation, which we'll get to in a little bit. So sometimes when you're doing things that aren't just digital, you need to give that a little bit of thought. So, perhaps not especially clear from the diagram, but there's a bunch of pins that are general purpose, and you can do input and output through those. There's a couple here that you can use for analog input. There's actually 4 of them, look. And maybe PWM. You can use all of them for PWM as well, this one, which is handy to know. Anyway, so if we wanted to use an analog input to sense the environment, then we've got basically these 3 here to play with. Okay, so pin 31, 32, and 34. If we go to the code, immediately it's telling me it's using a different pin, so now that's making me think. Maybe it can do analog digital conversion of more than just one. Well, let's give it a go. Why not, eh? Okay, so what we need is to connect something from pin 26. So that's going to be 1, 2, 3, 4, 5, 6. Pin there. We need to take some power from somewhere. So ground is pin 38. And the 3 volt out is pin 36. Okay. And then what we're going to do first of all is we're going to cheat first of all. We're actually not going to have any kind of analog input. We're just going to run the script and see what happens. And at the moment it's giving us a value. It's printing up. I don't know if you can see that. That's tiny text. Can you read that all right? And what I should be able to do is I should be able to, by touching this against either the ground or the VCC, we should be able to change the input for that pin. It's not working. Why isn't it working? Bear with me a second while I try and figure out what's going on there. I'll tell you what, one thing we can introduce at this point, there's some pretty good documentation on how you can let's use analog input 26.
case study on it. I was like, but it was quite funny. I really just regular, So, because right, you want to hear.
I've got no idea what's happening.
So, it's like the safe, there's like a very small version of it.
Oh, I've got an idea. Let's try something else.
It's like so much more charting cable. I was like, well, like OMG cables would be like this far. They would be like pissed off that I like compared to shit. Someone else, like, this one guy had been like developing them for years. And I was like, yeah, they're like a cheaper version of that. Yeah. I was like, oh, so there's a cheaper version.
Does it still work? Because that's not quite good.
Yeah, well, like, a lot of like the stuff is expensive, and I guess like made it cheaper price. Like, yeah, so I was thinking.
No, it's not the same.
That's really strange.
It's like just cut up all the inside.
I think the rubber duck is like super expensive, and then like
controlling the monitors.
there's other versions.
So it's set interface and a Wi-Fi network you connected.
Okay.
And then you can upload whatever.
We'll figure out what's going on with that in a minute. Okay.
Then we'll go down to the
No, goodness me, though. No. Did I tell you about my laptop and my phone? Okay. Anyway, we can take my word for it. That does actually work sometimes. Actually, do you know what? We kind of need to get that working for the next stage. I'll tell you what we'll do. Who wants to play with one of these? Yeah? Show of hands, sorry. 1, 2, 3, 4.
My brother wanted to use that one has a Wi-Fi chip on it as well.
Oh, wait. If you want to take it, have you got USB cables?
No,
You can.
USB cables. Can you get funny set up and get the microphone?
It kept crashing, but I think it's just because it's plugged in.
Oh, okay. Are you running Python 3.10?
I think it's actually 3.11.1.
Okay.
I don't know if that's,
Well, so the reason I ask is I know that there's a bug with the Python TK stuff on Python 3.8 that makes Thunny crash. So I don't know whether that's related. So if you get that set up while I try and sort this out, I'll be back in a second.
Jesus Christ.
Averaging.
Oh, so it's saying it wants to install all that.
I didn't really want to have to bother doing the lecture.
Well, it's like it's on the table, it's not
Like,
I know
I never
with that error.
Oh, wait.
like at Xavier and at the January.
So I just tried to go from Philadelphia to
Ground.
Oh, for the first one.
there we go.
Yeah, but it's probably it's going to take a couple of minutes.
So if you don't have one, if you can sort of try and crowd round someone's screen that does, sort of get a look at what they're doing.
I can put this in the middle somewhere.
I just half the day I just spent researching this
Okay, just redirected.
Like, people like talk about this.
I think we're just going to give it a minute. You're probably just trying to. Yes, we pressed the button.
Okay.
Don't press the button.
Now we wait.
It might press it now.
You should have the flash it.
Just do the flashy one. So copy that there once. I need to go a little bit. So I was going to start with
You sure it's working? Did you hold the button when you put in you and then you and did.
And then I see where it says downloading. Wait for it to download.
Well, downloading variant info.
Yeah.
Yeah, okay. That's what I thought. Okay.
You just hold that hold.
Yeah, it'll be like a CMOS clear.
Netflix technology stuff.
Or not CMOS,
No.
they don't have like the volatile. What is everything for your brother?
What's the word? Thank you. Thanks for doing that. Just put them in my bag.
No, nothing.
Okay.
Wait, for
Yeah, I didn't.
sound.
Yeah, I don't think that was annoying, but it was a bit like a.
Wait,
Maybe it was
right
a bit
before.
like
Okay, that should be it.
I was like, oh, if you keep listening. Yeah.
yeah. That's probably better.
He was very happy to talk about it though.
Yeah.
So are you doing it off like your phone's incorrect?
I think so, yeah.
Okay, maybe I should do that then. Because that's going to be way faster.
There we go. Right then, so let me plug this back in.
I have no idea. 10 LED. What was the other?
So,
It has no attribute out. It was lowercase. So it's
oh, not phone. You only G listen.
So to show what's going on here,
I copied this one really
I've got a lead plugged into pin 26 on the board. The other end of the lead is an analog input. It happens to be a
this is
it's not working now. It happens to be a rangefinder. So, like, you know, when you're reversing in your car, you get closest to the wall and it goes. It's one of those. And so, when I'm a long way away, you get a small input. As I get closer and closer and closer, you start seeing the numbers go higher and higher.
Oh.
Is there a way to correlate that to an actual distance or not?
Yeah, so part of the spec sheet for these, when you buy them, will show you the curve of input strength against distance.
So you can
okay.
that was a curve though, rather than a straight line.
Yeah.
That makes it a pain in the ass.
It is a pain in the ass, but it's cheaper to do it in software than to smooth it out in hardware. Okay, so that.
Light or sound versions of the range detectors.
Yeah, so this one here is infrared, but you can get ultrasonic ones as well. Okay, so what the advantage of infrared ones is because an infrared LED doesn't take a whole lot of power. You can have a low power device that gives you that thing. Now you can see how useful that would be if you've got a robot. You know, you might want to have some kind of collision detection. Well, there you go. You've got a built-in collision detection thing. So, if any of you are playing around with your thingamajig later and you want to try an analog input, just nick that from me, basically. I've got more. I've got a couple of each thing, I think. I just like grabbed a bag of stuff. I'm like. So it doesn't have to be one of those. It could be, for example, it could. I'm missing like a whole bag of stuff. Oh, it's over here. Look. Hey, I told you I've got some more. Look. There's another one here if anyone wants it. So it could be one of these. So you know when you're like using like old school devices and there's a big like chunky knob you can turn on the front. This is the back of a big chunky knob. It's just a variable resistor. And what we can do is plug the wires from that into our circuit board. And then when we turn the dial, it will change the input as well. So let's give that a go. feel free to carry on talking among yourselves because it's going to take me a couple of seconds to sort out. So I'm unplugging the rangefinder. There you go.
Yeah, the arrow was saying
on my laptop.
I didn't bring any pliers either. Like, what's the matter? Have you?
For the live audience.
I came from like a background beforehand, and that's pretty trash.
The exact same
Very
thing.
janky compared to
Because I that's quite funny. Because mine was just a doorbell that you.
Why do electronic engineers always have bad teeth?
this thing just constant jumping.
So the way these things work, if you've never used one before, there's like a strip of resistive material built into them, yeah, and then there's a sweeper that goes across the length of the material, and then depending on how far along you are, the effective resistance between either end and the bit that's sweeping changes. Okay, so if you put one side of it on your VCC and the other side on ground, and then this on the input of the thing, then as you turn it, you'll change the voltage on the input pin. That's what's happening. So let's wire this up and see what happens. And this is a tiny sibling of these, which is this. Pass that around. That's what we usually call a trim potentiometer. It's exactly the same thing, but it's in a tiny package. And often, if you've got a bit of electronics and you want to be able to tune something, you'll find that on the board, so you can tweak the voltage.
Radios, aren't they? Amateur radios.
Yes,
this
yes,
is
exactly.
Goodwin input for spinning.
So I'm going to plug the middle lead from this pot onto the pin that I was using a second ago. On one side, I'm going to put it onto the voltage supply, the other side on the ground, and then hopefully we should see the values changing when I turn the dial.
Pretty sure Lucas is there.
It looks like a lot of fun.
Hang on.
Also, we can only scan it remember.
There we go. So now if I turn this one way, all the way down to almost zero, and I turn it all the other way, all the way up to the top. And so just by turning the dial, I change the input. Okay. Right, so that's analog input. What we can do now is we can join up the analog input and some kind of output, right? So probably a good time to introduce the idea of PWM. Has anyone heard of PWM before? Okay. How can I best demonstrate this? I know what we'll do. We'll take the blink example that we used to start with. And what we're going to do is we're going to make it blink faster and faster and faster, and you're going to see what happens, okay? So here's a blink example, ripped straight off from the Raspberry Pi website. We're going to press play on this, and let's go back to the camera. I tell you what, they should always have chairs when you do this, because this is the first time I've done this talk and there's been a chair.
So much nicer sitting down rather than bend over.
Absolutely. So you can see the light blinking on and off there, yeah? So let's change the frequency from 2.5 hertz to 5 hertz, right? And it's blinking faster. What happens if I change that to 20 hertz? Blinking faster. What if I change it to 60 hertz? Can't really see that it's blinking anymore. It just looks like it's on, but kind of dim. Can
you tell in real life this is blinking?
I can just because it's toggling.
The camera on that.
That's right. Yeah. So it's blinking at 30 hertz because it's toggling at 60 hertz. So if I double that again, you can barely see with the naked eye, and if I double that again, ain't no chance, right? But what you'll notice is that that's not as bright as when it's on slowly, right? And this is useful to illustrate this thing called pulse width modulation, because when you're doing digital output and something's on or off, it's easy to see what's going on. When you're doing analog output, actually it's not giving you like a sort of voltage in between. It's giving you full voltage and then none, but it's turning it on and off really, really quickly. And how long the on is compared to the off determines how powerful the it's like a duty cycle thing, right? And so when you've got something like an LED or a motor, there's a couple of reasons why you'd want to do that. The first is that LEDs, the colour temperature changes with the voltage. So if you want it to be the right colour but dimmer, you have to cycle it on and off. With a motor, if the voltage is too low, it's more likely to stall, as in stop turning, and then that can burn out the coils on the motor. So with nearly all electronic and electromechanical things, it's better for it to be on or off than it to be sort of on, and therefore pulse width modulation is how you control them, right? As an aside, if you're in an electric car or on a train or something like that, and you hear the sort of sound, that is pulses of power going to the motor. Yeah. Right, so let's illustrate that. We're going to take the example that we've just used where we're reading an analog input, and we're going to actually set up an output to write an equivalent value. So where are we? It's a ready-made example, so let's use that one. But what I'm going to do is, instead of using the LED on the board, I'm going to use the built-in one because it's handy. Okay.
I'd like to make it better.
So do you see the LED on the board? It's changing with brightness as I'm turning the dial. And the way that works is this. Here, look, I'm setting up the pin as a PWM pin, so pulse width modulation. I set the frequency at which it turns itself on and off, so that's 1,000 times a second. And then the duty, as in how much on against how much off, is defined by the stuff that I read from the analog input. And then as I turn the dial, you can see that the effective brightness of the LED changes just by me playing with the input.
So it's always flashing 1,000 times a second.
Yeah.
But just the amount is on.
Yeah, it might just be a teeny bit of... So it might be like 1 millionth of a second every thousandth of a second. Or it might be 1,000th of a second every 1,000th of a second, in which case it's always on.
Frequency to like 10.
It will depend on the hardware.
I'd love to see it flash at that point.
Let's give it a go. Oh, there we go, look.
Yeah.
There you go. That's a brilliant idea. Thank you. There we go. So you can actually see what's happening there. Good call. Thank you. Brilliant. So there we go. That's what pulse width modulation is. Now,
So I get paid. I don't get paid.
I don't get paid. And when you're controlling motors and things, that's pretty much all that's happening. Yeah. There's one more step, and I'll get to it in a little bit, which is that this is only sorting out how to set a voltage, and to make a motor go one way or the other, you actually need to change the polarity of the inputs on the motor. And for that, you use a thing called an H-bridge driver. I've got one of those here, so if you want to play with an H-bridge driver, here is one, and we can get that going in the workshopy bit if you're interested. Okay, so the next bit, and we're not actually going to do this because the phone I was going to show you is broken, but we can have a play ourselves. is we've used basic input and output here. We've done some analog input using stuff like the rangefinder and the potentiometer. We've done digital input using a button. We've done digital output using an LED. We've done PWM using an LED, and we could, in theory, do it with a motor as well. What about more complicated things? Like, what happens if you've got something like this thing here? This thing here is a little button board that will allow you to illuminate the buttons in different colours and have them pushed, right? That's a lot of different pins to use. Well, you might just bit bang loads of the different pins on the Pico, and that would work fine. What if it's even more complicated? What if it's like I must have something somewhere that's interesting. Oh yeah, here's a good example. This thingy here is a Bluetooth receiver. Yeah, so I can pair that with my phone and send and receive data through it. All right. Well, you need to have other interfaces, okay? And nearly all of the microcontrollers and boards that you can get hold of will have some kind of hardware support for common ways of doing stuff. So there will be UART pins for serial connections, and there will be specific pins for protocols like the Philips I2C protocol and stuff like that. And really, the main thing that you need to know is that almost always when you're doing that, there will be a higher level set of interfaces that allow you to do the thing. So you don't have to write your own code to read to see when the serial line's gone high and wait X milliseconds and then wait to see if it's gone low and then figure out how many bits you've seen and whether or not that corresponds to such and such a number. You can normally just say, actually, I want to read some serial bytes and I want to set the baud rate to this with, a parity bit and whatever. And so, like, almost always there are abstractions, and, with the Arduino library, with the MicroPython stuff, pretty much anything you're going to be using, there are things that help you to do that. Okay. But that last piece there, there are more high-level ways of doing communication, is the stuff that bridges the gap between something like this and something like the Pico or the Arduino. Because as soon as you've figured out how to do a serial connection, and we'll set one of these up in the workshop bit, you can then have a general-purpose computer talking to a microcontroller, which gives you the networking stack, high-level hardware interfaces magic of the Pi, and all of the rapid PWM, analog I/O, yada yada, that you get from a microcontroller. Yeah, and when you're building actual robots, usually you need both. You need both the high-level access to the system, but also the real-time and I/O capabilities of the low-level stuff. Okay, so we'll play with that in a bit. But basically, that's all you need to know. The next step is to play with it, right? So what we can do is, there are 3 laptops around the room. Yeah, so probably 4-ish people around each laptop, and we can sort of play around with some different stuff. Everyone can have a go, sort of try and get things working. Yeah? Does that sound good? All right. Anything else you want to know before I stop talking to the group?